Okay, so boundary conditions. So we leave the boundary conditions of electric field, magnetic field to the last until I finish all the electrodynamics series, because this is highly related to electromagnetic wave propagation, where we have impinging wave, and then there's reflection, there is transmission. So when the electromagnetic wave propagates through a surface, then the electric field and magnetic field, they would change. But there is also something that wouldn't change. For example, the charge. So on the surface, how much charge is there? It wouldn't just disappear, or some more charge just randomly come here for no reason. And then for magnetic field, it's the same. When the wave propagates through a surface, or there's reflection, magnetic field would change, but something wouldn't change, which is free current, because current wouldn't come out from nowhere. So it's really important to have these boundary conditions that link electrical field and magnetic field on both sides. They are going to be different, but there is a relationship between both sides, so that if we know the impinging if we know the impinging EM wave, then we can calculate how much is reflected and how much is transmitted. So let's first study the most simple boundary conditions, which are the ones in electrostatics. So we investigate the electric field. So we have a uniformly charged surface. Let's consider this to be like infinite. Then if electric field come this way and cross, it will cross the surface this way, then the electric field would have two components. One component is perpendicular to the surface. Another component is parallel to the surface. So we have two fields now separated by this area, separated by this surface. One is electric field above. So we have the electrical field above the normal component, and we have electric field above the parallel component. And then for the electric field below, we also have the electric field below the normal component, and then we have the electric field below parallel component. So how do we establish relationship between the electric field above and the electric field below? We still need to observe from Gaussian pure box. So we have a pure box that has area but infinitesimally small thickness. So the pure box will be crossing this area. Okay, so for the electric field that cross the surface of the two faces of the pure box, we have the above normal component and below normal component. And then for the electric field, if we observe this loop, then we will get the parallel component above and below. Let's look at them in detail. So first of all, we always have Gauss law for electric field. Suppose it's free space, we have electrostatics. Then Gauss law in integral form, we have the closed surface integral of the E field equals to the total charge enclosed divided by epsilon 0. So we need a closed area. So if we observe this pure box, we have the above area A, below area A, and they enclose total charge A alpha. So when we observe the area, the direction of this area infinitesimal patch is perpendicular to the area. So we are effectively observing this and this. So we have E above normal component multiply A minus E below component normal component A equals to here we have the surface charge density. So sigma A divided by epsilon 0. So y minus sign here. So the closed surface, we have this, and then the direction is perpendicular out, and then so one of them must be negative. So this is perpendicular out of the upper surface, and this is the negative of the perpendicular to the below surface. So in summary, we have E above normal component minus E below normal component equals to sigma divided by epsilon 0. So that's the first boundary condition. And the second property we always know for electrical field is that the curl of E equal to 0 for electrostatics. So this means if we do surface integral of the curl, this equals to the So if we do surface integral of the curl, this is equal to the closed loop, closed path integral, closed line integral, and this is equal to 0. So we need to observe a closed path. So what we can do is we can observe this path. The thickness is infinitesimally small, and then the width is L. So by observing this loop, we are establishing relationship between this and this because they are parallel. The thickness doesn't matter. So what we have is E above parallel components minus E below parallel component. This is equal to 0. So y minus the line integral is a loop like this. So one of them must be negative. So here we have E above parallel minus E below parallel equal to 0. This is the second boundary condition. So in summary, if we express this as vector, we have E above vector minus E below vector. We have sigma divided by epsilon 0, and then the unit norm vector, so pointing up, perpendicular to the surface. We only have the normal component of the E field. So second set of boundary conditions is for magnetic field. So we first investigate this in magnetostatics. So similar to electrical field, when magnetic field cross the boundary, we have the normal component and the parallel component. So we have B above parallel component and B above normal component. And then for the below, we also have B below normal component, and then B below parallel component. So how do we observe this? We also observe this from pure box, like it's like a microscope. We observe just one small area of this infinite surface. So we have a pure box. And then we have, for magnetic field, we have the surface current. The surface current density is given by K. So now the first property we always have is divergence of B. Whatever is moving or not, we have divergence of B always equal to 0. There is no magnetic charge. So the integral form is the volume integral divergence of B d tau. This equals to the closed surface B, and then dA, this equal to 0. Okay, so this direction is perpendicular to the surface. So we have B normal component above minus B normal component below equal to 0. So B above multiply the area, B below multiply area, that would be 0. There's no magnetic charge. And then we also always have unparallel, which tells us the integral form is the closed line integral B dl equals to mu 0 and then total current enclosed. Okay, so for this, what we observe should be a loop. So we observe this loop. Then we will get relationship between the parallel components. So what we have here is, so if the width is L, the thickness is infinitesimally small. So I have B above L minus B below, parallel component L. So this equals to mu 0 K L, parallel component. So in summary, we have B above parallel component minus B below parallel component equals mu 0 K. So this is second boundary condition. This is first boundary condition. So in summary, if we express both of them in vector form, we have B above vector minus B below vector equal to mu 0 and then K cross N. So the current is flowing that way, and then N is perpendicular to the surface. K cross N, we get the parallel component of the magnetic field. So this is overall boundary condition. Finally, we need to investigate both electric field and magnetic field, the boundary conditions for both fields in electrodynamics. So let's look at electric field first. So we have a surface, but we have the free surface charge density. And then, so the surface above, we have epsilon 1. Surface below, we have epsilon 2. So these are two medium. It's no longer free space. So now we need to investigate, the electric field, the for the above, we have E1 normal component, E1 parallel component, and then for below we have E2 normal component, E2 parallel component. So we use E1, E2 here because later on the surface can be, towards any direction, and then this is more general than what we considered before. So now we also need to observe, pure box. Okay, so first for electric field we always have Gauss theorem, Gauss law, but it's generalized to linear media. So we have the surface integral of the electric field equal to the total free charge enclosed divided by epsilon. Okay, so if we move epsilon to this side, for when we observe the upper area and lower area, what we have would be epsilon 1 and then E1 normal component A minus epsilon 2 E2 normal component A equals to the total charge enclosed. So upper space and lower space, they don't have the same permittivity anymore, but they share the same free charge. They share the same total free charge enclosed. Okay, so if we delete A, we have epsilon 1 E1 normal component minus epsilon 2 E2 normal component equals to the free charge surface density. Okay, and secondly, we have another property which is the curl of E. Actually, here we have minus dB dt, right? So we have the integral form, which is the closed loop electric field dl equals to, so I actually do surface integral on both sides, but surface integral on this curl, we can call fundamental theorem for curl, and then this become the closed line integral. So on the right hand side we have minus d dt, and then surface integral b dA. So for this one, we are observing this loop. So this loop would have a width L, but its area should be infinitesimally small because the height, the thickness, is infinitesimally small, which means the flux here should equal to 0 because the width is infinitesimally small, the area is infinitesimally small, so there is no area integral that can give us value here. But there will be line integral here because of the width here has meaningful value. Okay, so what we have is E1 parallel component L minus E2 parallel component L equal to 0. So in summary, we have E1 parallel component minus E2 parallel component equal to 0. So this is the first boundary condition for the normal component. This is the second boundary condition for the parallel component. We have the E field. Now we need to do B field. So we also have a surface, but now we care about free current. So we have, mu1, mu2. So the permeability for the two areas, they are different. So now we also observe a pillbox. Okay, so for here we also have B1 normal component, B1 parallel component for the above, and then we have B2 normal component, and then B2 parallel component. So we need to establish relationship between them. So first off, we have the important property of the divergence of B field always zero. There's no magnetic charge. So the integral form, we have the closed surface integral B dA equals to 0, which means the normal component, they will be equal to each other. So we have B1 normal component minus B2 normal component equal to 0. So basically you multiply them by A, the area A, and then there is no magnetic charge. There's current, but there is no magnetic charge. Okay, so another thing is we have Ampere's law, but with Maxwell's modification. So we have the curl of B equals to mu J free. So free current density, and then plus mu epsilon dE dt, right? So the integral form is here you do volume integral, but you have you call the fundamental theorem for curl, then you have the closed line integral B dl. So this would equal to mu total free current enclosed. So this is not mu 0 anymore. This is not current enclosed anymore. This is mu and then total free current enclosed. And then plus mu epsilon d dt, and then the surface integral E dA. So for this loop, we are observing again here. So there's no flux that's equal to 0 because the thickness is infinitesimally small. So the area is going to be infinitesimally small. There's no flux here. But the width is meaningful. So we can establish relationship between the parallel components. So what we have is B1 normal component L minus B2 normal component L. So this equals to mu, oh wait, yeah, I made a mistake. So upper is mu1, lower is mu2, so we need to move mu to this side. So what we have is mu1, 1 over mu1, and then B1 normal component L plus 1 over mu2 normal component L. The normal component, oh sorry, parallel component. Parallel component here, this loop, parallel component. I'm really sorry. So this equals to total current enclosed, which is KF L. So L, you can delete all of them. So you have 1 divided by mu1 B1 parallel component. Oh, sorry, this is minus. So sorry, here minus 1 over mu2 B2 parallel component. This equals to the density. Let me check. Yes, the density. So so I have two more boundary conditions. So if we write this in vector form, then we have k cross n again. So k, and then cross n, we have the parallel component. So let's summarize all the boundary conditions. So first of all, we have the normal component for electrical field, E1 normal component, minus epsilon2 E2 normal component equals to the free surface charge density. And then the second, we have the normal component for B field, B1 normal component minus B2 normal component equal to 0. And then third, we have the parallel component, E1 parallel component minus E2 parallel component equal to 0. And the fourth, we have 1 divided by mu1 B1 parallel component minus 1 divided by mu2 B2 parallel component equal to kf cross n. So here, unit normal vector, which is perpendicular to the surface. So here we go. We have all the boundary conditions. So now we are ready to study electromagnetic wave and investigate how the electric field and magnetic field change when the electromagnetic wave, or we call it light, arrive at the surface, and then there is reflection and there is transmission.